preparation for the Chem 2025 midterm exam, I created a practice exam. It's not in exactly the same format as the actual. It is definitely tracking the concepts and the rigor of the actual, but it is not in multiple choice format. So in that sense, the actual exam will be easier than this one. We're covering Core 1 chapters 1 through 7, and I have provided you with a midterm resources sheet which you should become familiar with. In fact, please work through this practice test before you watch this video in which I work through it. Use the resources sheet while you're doing that so that you become familiar with what you have available to you. Notice that the resources sheet does not include metric prefixes. Your teachers have been trying for 10 years to get you to memorize those, and I'm going to do the same. It doesn't include the Greek prefixes, which you need to know when you're naming covalent compounds. And it doesn't include acid names. Now, you really don't have a great table of the common acids, and so let me put those here for you so that you have a convenient place. So what we're going to do is we're going to call these the common strong acids, and you should know these. You'll be highly functional to know these: hydrochloric, hydrobromic, hydroiodic. These are what are called the binary acids, and they are all named as hydrochloric acid, and then you just say hydrobromic for that one, and you'd say hydroiodic for this one. So those three are all in the halogen column. HF precedes this, hydrofluoric, but it's not a strong acid, so I'm not putting it on the list of common strong acids. So those are the binary acids. Then you have what are called the oxyacids, and for these, the strong ones that I want you to know are nitric, HNO3, based on nitrate, nitric, sulfuric, and perchloric. You'd say perchloric acid. And then chloric. Perchloric acid is based on perchlorate, HClO4 minus. Chloric acid is based on chlorate, ClO3 minus. There are only 7 strong acids. Here they are. It's probably easier to just memorize them. Moving on, let's look at the types of things that you need to know. Go through your vocabulary for the different chapters. I gave you 20 of these, so it's very convenient. At the end of each chapter, there's a glossary. Familiarize yourself with these terms. It's matching. I did 1-to-1, so it helps you out. Alright, now we're going to get into chapters 1 and 2. So here we did math, temperature conversions, significant figures, and density concepts. So I just kind of bundled them all together here under chapters 1 and 2. Alright, so if you want to convert 0.0015 picometers to micrometers, you need to first of all think, what's a pico worth? Hopefully you're saying in your mind that's, 10 to the minus 12. My pen is not very sensitive. Pico is 10 to the minus 12. Micro is 10 to the minus 6. So you have 6 powers of 10 different. You have to think about which one's the larger one. Pico is smaller than the micro. So if I'm moving to micrometers, my number needs to get smaller. So I need to go over 6. 1, 2, 3, 4, 5, 6, and then this number. But that was, of course, a very cumbersome way to write that number. So we had 8 zeros and then one more. So to do this in scientific, I would do 1.5 times 10 to the minus 9 meters. Micrometers. Okay? And that would be the conversion. So noticing it's 6 powers of 10, and then I'm moving to the larger unit, I've got to have a smaller number to go with that. Alright, if you're going to convert 1.4 times 10 to the minus 2 kilograms to milligrams, a kilo is worth 10 to the plus 3. A milligram is 10 to the minus 3. We're again faced with 6 powers of 10 difference between these prefixes. And so we're moving to from a big unit to a small unit, so my number needs to grow by 6. So I would say 1.4, it was 10 to the minus 2, I'm moving it 6, so I end up with the 4 power milligrams. Okay? If I have 1.4 times 10 to the minus 2 and I multiply it by 10 to the 6, it's 10 to the 4th. Number 4 actually takes quite a bit of thought. Arrange from smallest to largest. You've got two things going on. You've got numbers and you've got prefixes. So do apples to apples first. Turn these all into grams so that we are making an even comparison. So milli is worth 10 to the minus 3. So 10 to the minus 3 times 500 would be 0.5 grams. Kilo is worth 10 to the plus 3. And so this is really 9.9 grams, this pen. So this is the largest, this is the middle, and this is the smallest. They're actually already arranged from smallest to largest. The next problem we have is a density problem. Density of lead is 11.34 grams per cubic centimeter. Remember this handy thing. A cubic centimeter is a milliliter. They're synonymous. What is the volume of 25 grams of lead? That's question A. What is the mass of 25 mils of lead? That's question B. So we have our density relationship. Notice this is not on your midterm resources sheet. You need to memorize that if you haven't already. Density is mass over volume. In problem A, I'm giving you density and mass, and I'm asking you for volume. And in part B, I'm asking you for mass, giving you volume. Okay? All I'm doing is alternating which of these two variables is a given and which is an unknown. I'm telling you that problem A is where people make mistakes. Okay, so I've been teaching quite a while, and whenever I ask for a variable in the denominator, people make algebra errors. So here's part A. Density is 11.34 is mass, which is given, over volume. So volume ends up being 25 divided by 11.34. This is that crisscross and divide through to isolate volume on the left-hand side, so it's in the numerator. And when you do this, you get 25 divided by 11.34. You get 2.2, and what are my units? Either cubic centimeters or milliliters. Density is mass over volume. In part B, what is the mass given the volume? 11.34 equals m, the unknown, over 25. I'm just going to multiply these. 11.34 times 25, and I get 283.5. If I'm recognizing sig figs, which I should always do, I would round this. Let me hear my approximately equal to 2 sig figs, because on the incoming numbers I just had 2. Okay, on that guy. I had 4 here, but 2 there, so I'm limited to 2. Number 6, perform the following algebraic operation and type in the answer with the proper number of sig figs, ordinary notation, which means not scientific. Just write it out regularly. And using rounding rules. Our rounding rule is whatever digit we need to round to, we look to the right. If it's 5 or more, we round up. Okay? Here's my algebra that I need to do. And I notice it's multiplication and division. So what is the multiplication division rule? It is match the least of these incoming numbers for sig fig count. I've got 3, 2, 3. Because of this one, my answer will be reported with 2 sig figs. So punch this in my calculator. I get 55.6 times 0.014, and I divide it by 4.34. My calculator says this: .1793548.387. Okay, that would be ridiculous to put that as your answer. It shows no regard at all for sig figs. You get 2, so this trims to what? Well, I get 2, so I look to the right. Is it 5 or more? It is. I round up. 0.18. That's your answer. Convert 1.8e to the minus 4, which means 1.8 times 10 to the minus 4 to an ordinary number, meaning take out the times 10 to the minus 4. So I go left 4. 1, 2, 3. 0.00018 is your answer. Convert 0.0045 to scientific. Here I want the power of 10. I'm going to turn it into 10 to the minus 3. Scientific is always 1 digit, decimal, the rest of the number, times 10 to the minus 3. And scientific notation is nice in that whatever is in the base is always significant. Number 9 is a temperature conversion problem. You do get these formulas on the exam, on the resources sheet. So just put them over here. Fahrenheit is 1.8 Celsius plus 32. Kelvin is Celsius plus 273. So in this problem, I'm given Fahrenheit, so it would be 40 equals 1.8 C plus 32, so I'd subtract 32, it would be 8 equals 1.8 C, and if you punch this in, 8 divided by 1.8 is 4.4 degrees Celsius. So therefore, my Kelvin is 273 plus that, so it'd be 277.4. Let's move on to Chapter 3. Chapter 3 was a conceptual chapter. It dealt with what is chemistry, the atoms that make up everything, what is heat, temperature, what are the phases of matter like from a kinetic molecular theory perspective. So let's go through these questions. Chemistry is called the blank science. It's central. That's because we say atoms compose everything. What's the difference between temperature, which is average kinetic energy of a molecule? So if I'm at 100 degrees C versus 10 degrees C, 100 degrees C is a higher temperature, so it's saying that the molecules are moving faster. On average, it's a reflection of what the atoms are doing. Heat capacity is the mass times the specific heat. So it's based on the kind of material you have. Specific heat is a characteristic of the atomic structure in the material. It's how much heat is needed to raise 1 gram of material, of this particular material, 1 degree Celsius. So, for instance, water is unique in that it has a very high specific heat, meaning it takes quite a lot of heat to get it to go up in temperature, versus aluminum, which has a very low specific heat. So we put a aluminum pan on the stove and it's instantly hot. Then heat capacity also has to do with how much material you have. So if I have a big tub of water, it will take longer to warm it up than if I have a small teacup of water. So heat capacity captures this whole idea of how the atoms are arranged in the material and how resistant they are to heat changes, and the quantity of material that you have impacts the amount of heat that can be absorbed. Then finally, I guess I should have had this a little earlier before the heat capacity, heat is energy energy. That's a very important concept. Heat is energy that flows from hot to cold. If you don't have a temperature difference, no heat will flow. Number 12, conceptual questions about the kinetic molecular theory and states of matter. The KMT, the kinetic molecular theory, is thinking on the atomic level. What are the atoms doing? Here I have an image of the different phases of matter, and the KMT is basically expressing what we see here in these images. When we have the solid phase, we're saying that the atoms are close together and they have bonds that have formed between the atoms, and that all they're doing is vibrating. They're very rigidly in place. When we increase the temperature, we're giving the atoms more energy, and they end up having more kinetic energy and less bond energy. And so as a liquid, where they're in this in-between state where they're making and breaking the connections between the atoms, not officially called bonds, we'll call them the intermolecular attractions. They're making and breaking these, and they have medium motion. And then as we continue to increase the temperature, we're moving into the gas phase, which is all about kinetic energy and no bond energy. And then we could energize still further, and we would have electrons leaving the atoms, and we become a plasma, which is an charged gas phase. So you'll have some conceptual questions about the KMT and the states of matter, which is what we've just covered there. Number 13, conceptual questions about the physical and chemical properties and physical and chemical changes. So the key thing is the atomic structure still the same in the material? If it's the same, then we have a physical change. If the atoms have rearranged and we've made new bonds, then we're dealing in the chemical stage, okay? So this is atoms break and make new bonds. And the physical properties, we're describing what the material looks like. Chemical properties, we describe its reactivity. For instance, the combustion of gas. We might put gasoline in, we get carbon dioxide and water out. That would be a chemical property, that it is combustible with a flame, that we would then have this chemical reaction happen. And physical changes would be solid to liquid to gas. It's the same material. I could have ice, then liquid water, then steam. It's always H2O the whole time. That's just a physical change. But if I split water into its hydrogen and oxygen components, and to balance this, I'd have 2 waters splitting to form 2 hydrogen gases and 1 oxygen. That's a chemical change because the atoms have rearranged. Number 14, if 36 grams of water is split into hydrogen and oxygen gas, and if 32 grams of oxygen is trapped, how many grams of hydrogen must be produced? All right, just looking here at what's already written, we're saying we had 36 grams of this to begin with. We end up with 32 grams of that. We're saying with conservation of mass, this is basically a conservation of mass question. We can't lose atoms in the process of a chemical reaction. They're still there. All of the atoms that have ever existed are just rearranging with each other. So it must be that there are 4 grams of hydrogen gas produced to abide by the conservation of mass. Officially, it's conservation of mass and energy because it is possible to convert mass to energy according to Einstein's E equals mc squared. But that's beyond the scope of this course. Finally, to wrap up Chapter 3 and this video, identify the number of atoms in the following molecule of penicillin. Okay, so molecules can get quite big. Here we have 16 carbons. We have 18 hydrogens. We have 2 nitrogens. We have 4 oxygen. And we have 1 sulfur. And in a future chapter, Chapter 8, we learn to get the mass of this thing. We just multiply 16 times the mass of carbon plus 18 times the mass of hydrogen plus 2 times the mass of nitrogen plus 4 times the mass of oxygen plus 1 sulfur mass is the total mass of 1 molecule of penicillin. Not too complicated. The idea is the grand total is the sum of the parts. That's it for the first 3 chapters. I will continue on another video to keep the video length reasonable.